I am Marianna Parzych, and I am a data scientist with computer vision in DeepSense. And together with Konrad Czarnota, who's senior data scientist, also with computer vision in deepsense.ai, we will talk to you today about NeRFs and Gaussian splatting. We will share with you results and some insights from the internal project we were working on. The project concerned the synthesis of 3D scenes using NeRF technology. Some of you probably know what this is all about. For those who know, we can show it on the next slide. The goal of our project was to use NeRFs and a set of 2D static images of some scene or object, like you can see it on the left side, to produce 3D synthesized scene. I can now present you some agenda. We will first present you the motivation for this project. We will talk about what are NeRFs, how they correspond to classic photogrammetry. We will discuss some issues about data collection, present you methods based on the NeRF, and show you the demo. And then Konrad will present our work on Gaussian splatting. So let's start with motivation. This NeRF technology is relatively new, but still there are some use cases already to be explored. First, special effects and virtual reality for films and entertainment. Another thing are 3D models for online shopping platforms for e-commerce. You can imagine that a customer would be allowed to see products in 3D from every side, every angle before making a purchase. 3D models of organs and tissues for medical industry, for young medics to learn before they get hands on our bodies, and for patients to learn about, for example, their illness and medical procedures that will be conducted for them. Another industry is education, where NeRFs can be used for interactive teaching aids, virtual training environments, for entertainment, and selling tickets for mass events when we could show the customer what exactly will he see on the concert or a match he dreams to see. And also 3D models of some existing monuments or tourist attractions, and virtual reality and to advertise cities for all over the world for tourism. And what is maybe most interesting for us, for our industry, is generation of synthetic and labeled data. So now, what actually are NeRFs? These are neural radiance fields. It's a new technique that uses deep neural networks to model 3D scenes. It was originally proposed in the paper you can see on the slide, proposed in 2020. And on the next slide, we can see that this is a representation of a 3D scene. NeRF is a deep network, and its input is a location of a camera and its viewing direction, and the output is a radiance, prediction of radiance for each point in space. And this network is trained with the use of some finished set of 2D images. After it's trained, it can be used to render any new view of the scene from any camera position. And maybe some of you now think that, well, it's not actually new. We know it, it's photogrammetry. Well, there are some differences. First thing is photogrammetry is well established, not very new, have been around for years, and there are a lot of tools and information and everything. Photogrammetry is based on traditional methods, needs a great number of images, and those images needs to be very good quality. This is critical for photogrammetry, that images are not blurred, are not noisy, and they show every angle, every view of our object that we want to measure. On the other hand, NeRFs are new, are still developing. They are based on deep learning, so you will need a GPU to use them. They can be used with fewer images, and those images can't have some noise or distortion or missing information, because NeRFs will partially compensate it. First studies comparison shows that NeRFs allow for higher accuracy than photogrammetry for large object and complex shapes and textures, while photogrammetry is better for small object with sharp edges and fine details. But the most important difference is that photogrammetry allows us to create a 3D model that measure our object and can be further used in some applications, some 3D scenes generation apps. And NeRF is a representation of a 3D scene by a deep network. So this output, what we get in the end, is the most important difference between those two techniques. And now I think Konrad will tell you some about data collection.
Yes, so the most important thing is that this is very easy. So basically, you can record a video, and just a regular smartphone camera will do fine. This is what we did. The most important thing is to move slowly with the phone. So we want to avoid any motion blur. We want to have the high coverage of the same areas between the frames, which are one after the other. It is good to capture this in from the each possible angle. So basically, as Marianna already mentioned, some parts of the scene which were not seen might be hallucinated or approximated, and NeRFs do somehow manage it, but it's better to think about it earlier and like provide all the necessary views. Zooming out and in to an object in a sense that you come closer and farther with a camera helps to catch finer details of an object. And it's usually better to focus on one thing in the middle. This is what works better. NeRFs usually do handle like big scenes, but you have to keep in mind that it is at the cost of like higher memory requirements, and the quality might not be the same as with smaller objects in the middle. So all of those points are true for both NeRFs and 3D reconstruction. But for the 3D reconstruction, you have to be much more careful, because like even small blurs, reflections, or shadows can cause the algorithm to fail. And we have the examples to show you. So basically on the left, you can see the image from an original video. At first, we ran one of the algorithms called Mushroom, if I remember correctly. There were like 42 images, and we didn't do anything with them, and we get like this thing in the middle. It's even hard to say what is it. But after reading some comments from other people, we find out that blurred images can cause this kind of effect. So we manually deleted like 14 images, which we thought were responsible for this case. And it turned out that the model that we obtained, the one on the right, is much better. So this is something you have to keep in mind if you plan to do the 3D reconstruction, that the images need to be of a good quality. And back to you, Marianna.
Thanks. So there are a lot of methods based on NeRFs. It was originally proposed in 2020, but already has many modifications and improvements, like Nvidia's Instant NeRF or MIP NeRF. And we also observed two interesting directions for NeRF. One was few shot or even one shot NeRFs, and other was NeRFs with control. Those solutions are not yet developed enough to be used in commercial projects. Results are not good enough, code is unavailable or still under development, but we think it would be beneficial to check on those ideas and papers about them after some time. I think they would be mostly useful for the synthetic data generation when they are ready. And now I would like to show you a demo. On the next slide, we can see that we will be using NeRF Studio. It is a framework that allows us to use many different NeRF-based techniques, and there are ready-to-use scripts allowing to perform end-to-end pipeline. So data preparation, creating of NeRF, training, testing. And here you can see the example from our ULAM room in the office. We were using NeRF Studio and NeRF Facto model. Let's move on. Here you can find some easy comments that can be used to prepare, process the data, and train models. Everything is available in the command line. And then when you train or evaluate your model, you can check the results in the web viewer, regardless of whether you are working on a local or a remote machine. And on the next slide, we have the demo. Yes, you can see the web viewer here. Those images are the images we did for the training in the places that were computed as the camera directions. You can set some parameters of training here, for example, output type, but most likely you will use it to generate results, for example, rendering. So on the preview, you just set the view you want to use, you add the camera, you add another one, maybe some closer. And after we zoom out, we can see that we have a couple of cameras and the trajectory going between them. We can manipulate with it, see how our preview will look, and render. And then we get a command that we will use in the command line to render. We can also export point clouds or meshes from the web viewer. Okay, we tried three NeRF techniques from NeRF Studio. We didn't use original NeRF because it is known from literature that it's slow and its modifications are better. So we used NeRF Facto, Instant NGP from Nvidia, and MIP NeRF. We use standard trainings on default configs proposed in NeRF Studio. However, we trained MIP NeRF only in 27% because it took a very long time. Those 27% took like a day and a half. So we decided it's enough and it should or trained in this time, or we cannot use something that is training so slowly. And we evaluated our models. Ground truth images were compared with renders generated for identical to those ground truth images camera positions. And we used PSNR, signal to noise ratio, which tells us how many useful information and we have on the image in the and how many noise we have there. And also SSIM, structural similarity index, and learned perceptual image patch similarity. Those two metrics show us how similar images are, how similar is our render to our ground truth. And as you can see, instant NGP was the best one. However, NeRFacto was also quite alright, but faster. And now we can look at those results. Yes, for me, for my eye, NeRFacto and instant NGP are quite similar and both nice. And as you can see, MIPNERF didn't learn anything useful in this day and a half. And it will be all about nerves, so I will now introduce Konrad once again.
Okay, thank you. So, coming to the Gaussian splatting. So basically, this is a different algorithm doing the same thing. So basically, it takes some images and outputs a scene, and it's more like a view of a given scene. This time, it's not a neural network. This is only like an algorithm which does the optimization. It basically uses splats, and what a splat is, this is those are like 3D points associated with a Gaussian looking function that says how to blend colors from close area. So on the left side, you can see the picture from the paper, which is like the theoretical view, how it should look like. And on the right, this is actually from the real reconstruction. We have some grass, and on some part of it, we can see those like spherical things, which are not as many of them on the left side and on the right. So you can see how it actually works. And then when we try to like sample the scene, the rays are coming through a lot of those Gaussian splats to actually get like the true colors. So it is not using a neural network, but still for the process of optimization, it needs a proper GPU. And for the real-time usage, when like going through the scene, you need to have at least RTX GPU. For like training and offline rendering, the older cards are fine, but for the real-time rendering, authors suggest using the newest available options. So here we have some key points from our research. So the reconstructed scenes are very good. We think they are better than what we get from NeRFs, and we use the same scenes. The optimization process is done per scene. So NeRFs usually did the same thing, but there were a few that tried to generalize. So, for example, they were trained on people, and they were told to like reuse, like trained on a few people and then run on something that was not seen. But the results for us were not that good, so we didn't even pursue this direction of research. We focused on the optimization per scene, which means that you cannot really reuse those models. They are only for one concrete scene. The required GPU memory depends on three things. This is the number of images, the resolution of those images, and the scene area and complexity. So basically, the first 2 points are easy to understand. The third one is a bit tricky. So basically, if you imagine like an object in the middle of a room and like the walls are white, then this scene can be thought about as easy. So you don't have much features. But if you take the same thing, like the same object in the middle, but on the walls you will have, let's say, a painting, then the scene gets more complex, and the memory required to actually represent this scene is much higher. And it's very hard to actually like predict how much you will need to cover the scene. In our case, we used like 300 images, and you saw those scenes. Like one was with this deepsense dice, and the second in the office. They were quite small, and we were able to run the optimization on like one GPU with 8 gigabytes of memory. So it worked, but when we tried to like make it a little bit bigger, then we already had the out of memory errors. So this is something that you have to keep in mind. There is a way to play with the parameters, like the number of spots, which of course will decrease the memory footprint. But at the same time, we tried it and it didn't work in our case. Like we were able to render bigger scenes, but at the same time, the quality was much worse. So in our opinion, it's better to decrease the number of images or to decrease their resolution instead of playing with parameters, unless you have like a lot of time and you can check, because there are a lot of them and it's not easy to like change them and get good results. The last point is the visualization. So the authors use external tool. It's called Cibr Viewer, and it only works locally, which basically means that if you run the training and the viewer on remote machine, you have to forward the X protocol through SSH to actually interact with the scene, which of course introduces a lot of latency. And to move the scene, it's hard to like interact with it, because we had like 1 FPS, something like that. So this is somehow usable, but it's very hard. And in case of NeRF Studio, it was much better. So here we did a bit like more experiments. First of all, we compared ourselves to Instant NGP, and which is in the bottom row. Most of the Gaussian splatting runs were better. For Gaussian splatting, we first tried different resolutions and different number of images. So basically, 50 images is still not enough, I would say. Going to 150 or 300 is something that should help you a lot. Actually, authors suggest a number between 200 and 300. We wanted to see if like going with only a few images will be enough. So we decreased the number to 10. At the same time, we were able to increase the resolution of the images, but still like the higher resolution and a lower number of images didn't work that well. So it's better to stick with more images of lower resolution. Something about 1,000 by like 500 should be fine. And we tried to increase the resolution while keeping the number of images, and at the same time changing only one parameter, which is responsible for the densification of the splats. So basically we made the algorithm use less splats and we thought that this is like not a very big change, and we were able to actually fit on this 8 gigabytes memory, but the results are worse than for those with lower resolution. So as I already said, we think that going with lower resolution is better than trying to fit and changing the parameters. Yes, so here are the like visual examples. On the top left, there is like 10 images, and you can see a lot of artifacts around. The object in the middle is somehow looking not that bad, but the whole area around is pretty much not good yet. 50 images is much better. We can see a few artifacts, like something in the top left corner on this image. There is something wrong with it, but it is very hard to notice it if you don't know how the scene should look like. And with 150 images, for me personally, I had problem with like distinguishing between the original image and the render. So basically it looks very, very good. And here we have the demo from the Gaussian splatting, the same room. This is the ULAM in the office. The video is not as smooth as in case of the NeRF Studio. That's because it was hard to like create this render, but I think it still shows that it looks very, very good. Okay, and we come to the summary. So basically those NeRFs and this Gaussian splatting methods, they are used to generate renders. Their goal is to look like good, like the scene needs to look good, but it doesn't provide us with any like point cloud or anything like that. For those kind of results, you need to use 3D reconstruction. And for the productive and comfortable work with both of those methods, we suggest you use a laptop with like graphical interface and a GPU card. And we recommend using Windows because this is something that most of those libraries target. So they provide binaries for Windows. We had to spend a lot of time making it work on Ubuntu on like remote servers. So we suggest it's better when you can work with it on a local machine. The topic is quite new. Many implementations are still in the development, and the tools are not stable. So this is something you have to keep in mind, that probably the things that you do not want to work at the first try. And in our case, we tested around 10 methods, and there was only one which worked at the first try, like exactly as it was written in the README. Most of them required playing around with libraries, changing some things in the code, etc. So you have to be prepared for problems. The methods using fewer photos, like they were a few that called that they claim that they are few shot learning. They didn't really work in our case. So on our scene, like passing the 3 or 9 images, it didn't really work. So we think it's not yet there. So trying something with only 10 images is still not possible. Even though like in the papers sometimes people show like good results, but I guess it's some kind of cherry picking. And well, the solutions are very interesting. We think they work considerably well. You just need to keep in mind that you need to have a good data set, like you have to collect the video in a proper way, and then it should all work fine. And that's it. Thank you for attention.